here, and I'll go a little bit slower on this, I think, or we'll end up a little bit sooner, as talking about roadway materials and things like dust control and what are some of the alternatives we have and why we have gradation requirements, things like that for roadway materials. And again, this is a whole science. There are materials engineers or people who live in the Caltrans lab there in Sacramento that seldom see the light of day. They're just always doing materials engineering work. And so it's a particularly important area because half the cost of a road can be in that 6 inches or that whatever paving surface or that agate surface you're putting down on the road. So it affects a great deal of the cost of a road, but it also affects the user comfort and how much dust and sediment comes off the road surface. So it has its environmental component as well as the social and cost component. So here's kind of what all we want to cover briefly here. We'll talk about just some of the surfacing alternatives that are available to us, dust and soil stabilization, which are very closely related for the control. Talk about some of the design issues dealing with agate because the agate is probably the most commonly used road improvement material. We use a lot of things called marginal materials. It's pit run material, not the best in the West, but it's locally available. And so talk about how to improve some of that or live with that. Quality control is always an issue when you're dealing with materials because higher quality costs more, but it performs better. And then last, I'm going to talk a bit about materials management because if you can find a source of material close to your site, you can save yourself a lot of money. But there's site development issues, there's environmental issues, they need to be reclaimed, and so there's reclamation issues. So we'll finish up with that. Okay, all the reasons. Why do we improve the road surface? Because it costs money. So we do it mainly. From a user standpoint, it makes the road more smooth. It improves driver comfort. It reduces the road user costs. These are operating costs. Less wear and tear and less maintenance on your trucks or vehicles. And you get there faster, so you have lower user costs. You do get there faster, so there's the time factor, which is nice with an improved road surface. You can reduce your short-term road maintenance needs, but you're often trading that off for some deferred maintenance or recurring maintenance, like with a chip seal. It's smooth until you have to rebuild it, 5 or 10 years down the line. From an environmental standpoint, if you can get something down on the road like an aggregate, you can save yourself a lot of erosion because you just have something that's not as subject to the movement from raindrop impacts. But like I say, these improvements come at a cost, and often it's a trade-off between what the initial cost is of improving the road versus the maintenance cost going on. When you look at costs of a road surface, it's really important to look at it from a life cycle standpoint. Are you going to use the road for 20 years, or is it an operation where you need it for 5 years? And then look at which is the cheapest alternative for that life cycle. Some of the problems with roads that aren't well drained or aren't well taken care of. Little few drainage problems up here on top. Where'd that arrow go? The arrow's giving me troubles today. I'm hitting the arrow, but it's not showing up. Oh, there it is. Sorry. Okay. Is this a drainage problem or a materials problem? And the answer is both. Down here is a drainage problem. Over here is obviously a dust problem. I threw this in from a friend who was working in the Pacific Islands. You're just muddy messes. Always fun. Not very good from the road user standpoint or the environmental standpoint. So these are problems with roads and materials. But then maybe more commonly, there are problems like this. Just how well is it performing on the road? And it also comes back to how the road is shaped and drained. Are you going to be getting potholes, corrugations, or washboarding? Just how smooth is it, which affects how fast you can drive on it safely. So let's look first at what some of these surfacing alternatives are. We've got a pretty wide range of things that you see. Of which probably this gravel road in this picture is probably the most common. Here are the range that I typically see on low volume roads. It's native soil, which native roads, which means no improvement to them. When you do get into your collective roads or roads you're using a little bit more, or in soft areas or in wet areas, you start putting down aggregate. And like I say, that's the most common road improvement, whether it be right on the subgrade or whether you put down maybe a base aggregate and then a surface course aggregate, or a surface aggregate and a subbase, something so you build up your structural section and end up with a rock aggregate or a gravel surface. And then something you see in a lot of countries, not too much used in this country, is something like cobblestones. Pavers, you see again used in a lot of other countries. They're used here and there in this country. In Europe, they're quite aesthetic. But they're not a cheap treatment. They're approaching the cost of an asphalt, but they have their own aesthetic appeal. And then you get to the asphalt surface things. The most common on our low volume roads would be just a chip seal. It'd be a seal coat on top of aggregate, and occasionally we go to the Cadillac version of a full asphalt pavement. But this is relatively inexpensive. This is getting progressively more expensive. And so this is appropriate for your lighter volumes of traffic. This is appropriate for your higher volumes. The aggregate, crushed aggregate, gravel, material pit run rock, they're probably the most common type of improvement you see on low volume roads because it's relatively inexpensive. You can, if you can find material close by, you can keep the cost down, and you both provide structural support and also remove some of the dust problem and mud problem once you put down aggregate. Here you have a couple other alternatives. This is a combination of both these pavers and some cobblestone used in some places in the Southwest. It's very labor intensive, so that's why you see it a lot in some developing countries, not so much in this country. Then there's road mixes, which was the old style of creating pavements. I've done a few jobs with them, and you can save some money over hot mix asphalts, but then there's more quality control issues. So it's not a technique that's used a great deal today, but it is an option. What is used a great deal today are seal coats, chip seals. We probably most of our collective road system in the Forest Service are chip seals. The arterials may go to pavement, but the collectors are often a chip seal. And what it is, it's an application of oil. First you have to have a firm base. And then you put an application of oil down, then an application of chips. We often do what's called a double chip seal. You put a second application of oil, a second application of smaller chips, and then you come back and roll it all and get a nice tight surface. And this can last, if it's well built, not abused, it can last from 7 to 10 years. Most of what look like paved roads in Africa or North or South Africa, Australia, New Zealand, most of their roads are actually chip sealed roads. They're not actually hot mix asphalt roads. But they've also have a lot of good quality control because they do it a great deal. And our problem is often quality control because we don't do it enough. Concrete used, it has its place. Some countries use it a great deal. Its best application is for me, it's either low water crossings coming through water or on steep grades. If you get into a really steep grade, it's always raveling. You can't hold the surface. Asphalt tends to shove, so concrete works. It's a great solution for a steep grade. If, for instance, you can't keep the grade down and you've got a quarter of a mile section of road that's pushing a 15 or 20% grade, which we normally don't want to build, but you've got them at times. Concrete, it's expensive, but works very well. And then the Cadillac, good old pavement, hot mix asphalt. And like I say, usually, most of your county roads, arterial roads are where you move to the hot mix asphalt. The most expensive, but it ought to be good for 20 years if it's properly built. There, this is like a cough, sputter, sput. This is what a road can look like if you're driving behind somebody and it's dusty. Unsafe situation if you can't see what's going on in front of you. You can see a little bit better what's going on here behind a logging truck or looking out a windshield or following somebody. There's three problems basically with dust. One is, it's unsafe. It's that you're both breathing or you can't see where you're going very well. It's hard on the environment. They say billions of dollars are lost in agricultural production because of dust along roads and areas. And it's also hard on the road because if it's dusting, you're losing the fines that you want to have in your road mix to keep the road surface tight. So it's damaging in a variety of ways. But there's a lot of things people do to keep dust down. What you don't want to do, and mostly like in our timber sales or areas where it's being used a lot, the road is being used a lot, we'll have some provisions for dust control. And probably, again, if you're one of the best controls for dust is if you put an agate surfacing on the road. And this is back east in, I think, the Allegheny Forest. If you got a agate on the road in a wet climate, dust isn't much of a problem. If you're in the west, you put agate on the road, you may still have some dusting, but it's much less of a problem than native fine soil. So here's the list of I think things that I know of that have been used for dust palliatives and also for surface stabilizers, stabilization. And if you get road surface stabilization, you do have the advantage that you're also achieving a certain amount of dust palliation when the surface is tight. So water is probably the most common treatment for dust control, but on a hot day, water evaporates. So if you have a lot of log haul, for instance, a lot of use in one short amount of time, if it's sustained day after day, water gets pretty expensive. For stabilization, we've used cement, lime, asphalts. Those are traditional. Often you'll put chlorides down, mag chloride or calcium chloride, because they absorb moisture from the air and then keep the road surface damp. And we've used at time, not too much anymore, but we used to use a lot of dust oils. So those are kind of the traditional products. And then there's the non-traditional ones, as I'll call them, ones that are lignin sulfonate is someplace between traditional and non-traditional. I know I've seen it used for years if it's available. But there's tree resins, there's vegetable oils, there's tall oils, there's the use of enzymes, clay additives, synthetic polymers. There's a lot of things out on the market that fall into the non-traditional category. Let me explain kind of how I feel about them here. The traditional stabilizers, there's a lot of good information. They're pretty tried and true, so I don't think you have to get into too much debate on just how to use them. They're pretty well documented. The non-traditional stabilizers, there's often specific application rates, how long they last, how well do you have to reapply the material, and so it's kind of the jury's out on a lot of them, and sometimes you have to get into some testing or evaluation to decide just which is really going to perform the best. The lignins, sulfonates, and the chlorides, either calcium chloride or magnesium chloride, have been used quite a bit, and so particularly they're water soluble, so they often tend to be more seasonal, but they do perform very well. Enzymes are one of those things. There was a question came up about them a couple of weeks ago, I think. I've seen variable results. They do perform best in clays because they actually bond the clay and make a denser product. They don't really cement it, but they facilitate densification. And I did a test section on some years ago where it was an aggregate road, and it really wasn't a particular improvement over the control section because we had good compaction on both. So enzymes, I think you need a pretty clay soil to be very effective, and we need to learn more about them, and I've just heard very variable results. And on all these, there's the state of the art or state of the practice is evolving. UC Davis, there's some folks there, and Federal Highway Administration are involved in getting better kind of database on a lot of these non-traditional stabilizers and better information on it. So sometimes it just takes a test section to figure out, because the real question is, first there's the initial cost, which is often easy to determine, but it's performance. How soon do you have to reapply it? And that's the $64 question. There's some pretty good information for like traditional stabilizers. There's good information. Canadians and Australians have some good information. This is a Forest Service publication that summarizes some of that. Basically, it's just taking a list of some of the products available and how they perform with different amounts of traffic and different soil types. Good information, good basic information, kind of compilation of other information that's out there. And the same thing, the Forest Service publication on soil stabilization does the same thing, and this is from a, this is hard to read here. You need to look at the full screen on this, but it's basically it's got different soil types and what products work best for those soil types and some sideboards. It's from an old Army publication, but it's reissued in this soil stabilization selection guide, which is again on your list of references. It's a compilation we did in the Forest Service a few years ago. But there's a lot of good information out there on this whole subject of soil stabilization, but particularly the traditional ones. Here we're mixing in with a grader, which is something that's often done with soil stabilization. It also can be an advantage for just even a dust palliative. If you put down more product and blade it in, you don't have to add it quite as frequently to the surface. Depends, again, on the amount of traffic, probably more than anything. More commonly for a lot of your dust palliatives is just a sprayer application. You can put it down as a powder, but most of them are liquids. Spray it on the road. This is some calcium or mag chloride that's been on the road for a while that tends to get kind of white, and I've seen very good performance with that, particularly for main haul roads or collector roads where it's getting a fair amount of use all season. And then you may have to reapply it, or a light treatment of it again in the subsequent years. Okay, let's talk about aggregates, move on to aggregates, because like I say, it's the most commonly used material for improving the road surface that exists for low volume roads. This is just, it was actually a just primary jaw, lightly crushed rock on this here, so it's not extremely well graded here. And there's several ways we approach putting rock down on roads, or rocking roads as we call it. First we may just fill the ruts the kind of poor man's approach, but it helps. We may put down a full structural section, which is something like this, which may be a section of 4 to 12 inches of an aggregate, and either over a sub-base or just on native soil. And so this guy's happier because he's got a better road here. And something we often do is just spot rocking. Now this is a real poor man's approach, but it's if you have a localized problem area, a soft area, we just put in a few cubic yards of rock, and then the rest of the road's okay. That's okay. Very appropriate for low standard roads. And like I say, it's what we call it spot rocking. It's just going in as needed. This is a little tedious, but what I'm trying to show here is it's an aggregate surfacing design, just a little chart or a graph. There's the Federal Highways, Forest Service, a number of people have developed different design procedures for aggregate thickness. I like this one because it's simple. It's based on soil strength down here, CBR of 3 being pretty poor soil, CBR of 12 being a pretty good soil, and traffic, the easels, that's equivalent single axle loads. And so it's traffic in this 4 to 6 inch range of aggregate, which is what we most commonly use. If you get into your weaker soils, you're moving on up here, which you have more in some of the Coast Range areas or the Pacific Northwest, you may be putting down 8 to 12 inches of aggregate. If you get into really poor soils, a lot of traffic, you'd need more aggregate. And at that point, you're probably going to a different surfacing standard. You're starting to look at maybe a seal coat or a pavement by the time you get to a lot of traffic. So it's an easy graph to use for taking a quick estimate of what might be a reasonable thickness of aggregate. And let me explain here. There's the aggregate, the concept of what you want out of an aggregate. This is if here on your left, it's what happens if you don't have any fines. It may be like marbles. It's great for drain rock because it's very permeable, but it doesn't have much density and you can't hold it together. It's like I say, it's like trying to drive on marbles. The other extreme, if you have over 25, 30% fines, is your rock is basically floating in a matrix of fine clay or whatever your fine material is. So the strength of this mix isn't the rock, the strength is this fines. And so if the clay, all that rock is just, and you see that if you dump rock into a kind of a mud hole and it just disappears and it's still a mud hole until you put an awful lot of rock into it. And so what you want and what gradations are based on is here in the middle. It's aggregate that's got enough fines, say 8 to 15% fines, that it's maximum density, but the rock is still pointing. You still have point-to-point contact here, 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 of rock to rock, so that's what's giving the strength. But it holds together, and it's particularly on the road surface. So this is what you want for an aggregate gradation. Just mix not too much fines, not too little fines, just right in the middle, kind of like what Goldilocks was like. And we often express this in what's called a gradation curve or a grain distribution curve. And what this is, if you work with engineering or materials, or an inspector for materials, you'll be familiar with this. But what you're doing is this is from coarse to fine, and this is percent passing, or the what's finer than any one given size. So you've got this what's called a gradation range of material that has certain percentage is coarse, and you go clear on down to a certain percentage that's fine. So you've got coarse to fine material that make a nice dense mix. And this is the range we work with on most of our road aggregates. But there is a significant other factor, and is the aggregate going to be confined under like a pavement or chip seal, or are you going to be driving on it right on the surface? And if you're driving on it, you really want what we call as a surface coarse aggregate. It's a little bit finer, and I'll show you the gradation or the specifications for that. But this will perform better than if you're driving on it. Gets too fine, it's dusty, you lose strength. Get too coarse, it's raveling, and you can't drive on it. So we want to be in this range for our specifications. And our specs tend to look something like this. And this is we're trying not to reinvent the wheel. So for base course aggregate, because everybody in the world uses it, we in the Forest Service tend to use like Caltrans gradations or Federal Highway gradations. But it's gradations from coarse to fine, so you have a good dense mix. But you don't have too many fines, and ideally you don't have much plasticity to it. So that's for base rock, and it's confined. It's, say, underneath a pavement. But if you're driving right on the surface, and your tires are contacting the gravel, you want to use what we call as surface coarse aggregate. And so this is a different animal. Not everybody has specs for this. And if you've ever put down base rock and driven on it, that's why it tends to ravel. It tends to the big rock tends to just get pushed off the road surface. So what you want on a surface coarse aggregate is pretty tight gradation, but more fines. They just help hold the whole thing together, maybe 6 to 15% fines. And typically you want some plasticity. You want a little glue to help hold it together. So this has more fines, some plasticity. Base rock has less fines and often no plasticity. So that's the way we approach it in the Forest Service here in the West. Well, folks back in Pennsylvania, this is something that Federal Highways and folks are looking at also. They very similar to our gradation. They're strong proponents of this 10 to 15% fines. Where you have enough fines in the material, so you have a good dense aggregate. And this DSA is dense surface aggregate. So I appreciate the fact that they're looking at it. What specifically is going to be used on the road surface. But the one place they tend to, where kind of some debate in, is they don't have any plasticity because they feel like that's it's a source of sediment and contamination. But also keep in mind on the East Coast it tends to rain more in the summer, so they can get away without having that plasticity. So if you're in a wet area, I'd say use this type of gradation. If you're in our drier west, I'd say tend to use more our specifications where you do have some plastic fines in them. Just a little refinement on use of surface aggregate. And the reason we care about this, there was the quiz question there. Why do you care about gradation of aggregate? That it mainly makes a difference of how the road performs. It's going to be smoother if it's nice, dense aggregate and a good gradation. It'll affect how much it tends to ravel. It'll affect if it tends to washboard more. And so, those are all reasons why you want a good, well-graded aggregate. It can cost more. I don't think it promotes traffic one way or the other, but it's more performance. And so it's this whole field of aggregate quality and management. It's kind of this thing of either you pay now or pay later. You pay up front and get better quality aggregate that performs better and needs less maintenance, or you get something that costs less initially, and then you have to put more money into road maintenance and maybe grading it more often. And that's a real trade-off we have on low-volume roads because you can go either way. Depends on the amount of traffic more than anything, and what materials are available. So let's talk about this materials that are available. That's the next main theme here. And often we use local materials and just try and improve them on site or make some improvement to them. We don't go to the full, nice, well-graded crushed aggregate. We use, say, a pit run material like in these photos here, and use a grid roller to roll over it and break down soft rocks. Say this was, I think, an andesite that was not real extremely hard, so we could break it down, and then you have something you can live with a little bit better. It's not as good quality aggregate as a good hard base rock or a surface rock, but it's inexpensive because it's close to the site. So we use marginal materials a lot on low volume roads, and I think they're very appropriate because they can be very cost effective. Mobile rock crushers. No, the contractor wasn't fighting with the inspector that day. This is just a first scale. This mobile rock crusher can take big bony rock like this and crush it down on site and then produce something that's from this size here, something that's down to here. And what you put into it is what you get. In some test sections we've done with this, the Forester or some types of these mobile rock crushers, you can probably produce an agate, this agate here, that may be half the cost of an imported agate, but again, you get what you pay for. It's either it has fines in a lot of fines in it, or maybe on the coarse side of it, but it's still cheaper than imported agate, but it doesn't perform quite as well. But at least you don't have really bony rock which are hard to maintain. Mixing coarse rock, something we use a lot in some of our coarse basalts here in the Sierras, where you're taking just the pit run rock, putting it down on the road, which is hard to live with, scarifying and mixing in just a poor man's road mix, and so you've got some fines mixed in with coarse rock, and it's something that's drivable. It's not the best in the West, but it's better than either the clay or the coarse rock, which tends to be like marbles to drive on and very difficult to drive on, particularly on a steep grade. When you get to the marbles, I think it's more like what you use in these speed ramps or safety ramps on highways where a truck can go off if it's out of control. These gravels slow you down. They're not easy to go through if they're just clean and loose. Blending. This is something I've seen done in a number of different countries, including the United States here, where you're taking, say, a gravel, and it's similar to the last photo actually, but a little different. Rather than on grade, you're doing it in a stockpile area where you're mixing in some clay, something like here, or clay, into some gravel, physically mixing it with equipment, and then producing a mix that is better than either the clay or the loose gravel. So it's a poor man's way of producing a suitable material. It's improving the characteristics of either material. Something that's not used too much in this country is this thing called CTI, Central Tire Inflation. And what that means is, as you can see in these photos, if you go to your full screen, you are, oops, where did my arrow go? Where did I? You've got here it is. You've got these tubes that are actually going down to the tires, so you can adjust the tire pressure in the vehicles. And what it does a lot for you on like an aggregate road or a soft road. With central tire inflation and reduced tire pressure, you've got this photo up here, really not too much damage after 50 truck passes. Without central tire inflation or going with high tire pressure, you tend to get much more rutting. And so the advantages of CTI are that you minimize rutting and minimize wear. You get less aggregate production, less sediment production off the road, less maintenance cost, that's easier on the driver. So there's a lot of advantages to CTI. And oddly enough, it's used a great deal in like in Canada and Mexico and Australia and Brazil, Russia. A lot of countries use it, but it's not that used in the United States because of a variety of reasons, and some of it's mixing going from off-road onto state highways, and you do have to be able to adjust your tire pressure. The point here is you've got onboard compressors, so there's some outfitting of the vehicles, but it's something that can ultimately save tire wear and wear and tear in the vehicle and perform well on the road. So quite a bit of research has been done on it. It's like that, to me, it's that better mousetrap. It's never really taken off here in the United States, but it has in many other countries. What do you do with big coarse rock when you've got just bony, cobbles in the road, which are, they're rough to ride on and they're a pain in the neck to maintain for a road surface? You can screen them out. You can just run your material through a grizzly, something like this, and get rid of that coarse material. Maybe use this coarse rock for riprap someplace, and then put this finer material, say minus down to 2 inches or something like that. Take everything smaller than 2 inches, put that on the road, and you can live with it much better. So it's a pretty inexpensive way to improve pit run material. Something we use a fair amount of, and it's another one of these uses of geosynthetics, both for separation and for reinforcement, is a layer of geosynthetic underneath the agate. The key thing here is that it's really only cost-effective if you have fairly soft soils, say a softness being defined as a CBR, this California bearing ratio, a measure of soil strength, of about 3 or less. If the soil is stronger than that, you're probably not generating a lot of benefit from the geosynthetic, but a cheap design or save you some money, an inexpensive fix. Here, for instance, this was on a main road here. Here, for instance, it was floated. This is geosynthetic over just a local soft area. It was the access road going up into a log landing. Just a local spring area. So rather than dumping in nothing but a lot of rock, they put down a layer of geotextile, put in rock, and then it just takes less rock and it doesn't just disappear down into the mud. In this photo, it's ready for a little bit more rock and started to heave up here in the middle, but it can save you a lot of agate. So it's really a trade-off. Which is cheaper, the more rock or the rock plus the geosynthetic? And then there are very specific design procedures that have been developed, and I won't go into the details here, other than as a function of the soil type and the amount of traffic. This is over on this side is the how thick an aggregate you need. So in this example, without geosynthetics or geotextile, maybe you need 24 inches of aggregate for this amount of traffic and this soil bearing capacity here. If you do put down a geosynthetic, particularly for separation, you can get away with a little less aggregate. And often, and if you really want stabilization, increased strength, both separation and stabilization, you might put down both a geotextile, which is the separator, the filter, and a geogrid, which adds the strength, and you can save even less aggregate. So with geotextiles, less aggregate. Without, you need more aggregate. So again, it's a trade-off of the costs. If rock is inexpensive, I'd probably just go with rock. If rock's expensive and the soils are poor, you can save some money at times in your design by putting in a layer of geosynthetics. And this is some procedures that are developed by the Forest Service. It's been the Federal Highway Administration. That book on gravel roads by South Dakota, LTAP, has good information on this. So there's different procedures out there on how to work with geosynthetics, and in that Federal Highway publication on geosynthetic design. Okay, quality control. I throw this in because you kind of get what you pay for, and with materials, you want to know what you're dealing with. If you want to use the material, you often will take a sample of it. You want to make sure it's representative. If you want 500 yards or 5,000 yards, you want to make sure you've got 5,000 yards and it's fairly uniform. You know how it varies. So the sampling part of it out in the field is, and then you spend some money if you're doing lab testing, so you want to make sure you've got what you're going to be using. You may run it through a series of lab tests, for gradation, for plasticity index, for LA Rattler, just a whole variety of tests that, for quality control tests. Um, you may want to need it for a Proctor or a compaction curve. So there's a lot of things you have to do in a lab to actually determine those properties. There are some nice field methods that have been developed for estimates, but if you're on a big project, you'll probably do it as the testing in the laboratory. One of the nice tools, I throw this in because a real handy tool we use quite a bit, and I think it's underutilized, is the dynamic cone penetrometer. Sounds pretty sophisticated, but in fact it's just a falling weight penetrometer where you drop this hammer, it hits against the like anvil here, you measure how many blows it takes to go into the ground, and so you've got an estimate of the soil in-place soil strength, and then there's real good correlations between DCP and like CBR, the California bearing ratio, which is used in many of your pavement or aggregate design procedures. So it's a fairly quick and inexpensive tool to characterize your subgrade and your aggregate and subgrade materials. This I firmly believe in. Having kids and working with people, I firmly believe in this. You get what you inspect, not what you expect. I'm an optimist, and like contractors, they're trying to do a job for you. They're trying to make money. If you have good inspection, then there's better likelihood that they're going to do what's required of them under the contract. Or same with just about anybody. So I say this particularly on low-volume roads because often there's not a lot of inspection that goes into some of our road work, yet we're spending good money for the roads, we're spending good money for materials, and so if we expect to get what we're paying for, you need some inspection. I'm going to touch just briefly here on compaction. Compactions, the advantages of compaction. Why do we compact? It's often specified, and what it does, it improves quality of materials. Almost any soil or aggregate, if it's compacted, will be stronger and perform better on the road. And it's the cheapest way to improve the strength of that material. So it's typically just a good investment. There are things about compaction. You have to use the right equipment. You have to have the right moisture to maximize the benefit of compaction. We may specify procedural, which means we're just going to run a 5-ton roller over it 10 times or 8 times. Or we may specify an end result. We'll want to have 95% of the maximum AASHTO T99 density or maximum Proctor density. So there's different ways we specify compaction, but either way we can make sure we achieve good compaction. Different types of equipment depending on the soil types, rollers, vibrators, steel wheel rollers often used in sandier soils, granular materials. Sheep's foot rollers are typically used in more clay type materials. This picture down here using a paver putting down aggregate was both to get, this is back at Penn State and their Center for Dirt and Gravel Roads, which is doing a lot of good research in these days on gravel roads and low volume roads. They use it for both maintaining good depth control and initial compaction, then come back and requires a little less compaction later on. But either way, these are all examples of compaction, and we often don't compact aggregate that we put down on roads, but to me it's very cost effective to do it. Probably one of the most common ways of compaction in the field, if you don't have a lot of equipment, is just with a water truck. You get that soil moist where it's just you can just kind of squeeze it and hold together in your hand, and then you run the trucks over it. And the challenge is getting the trucks to move back and forth across the road, because here you can see really good compaction right in the wheel tracks, not as good a compaction here where the truck haven't driven, so you've got to direct the drivers of the trucks to go across the road. But you can achieve pretty good compaction this way. And this is, if you work with compaction, you're familiar with these type of curves. All they're showing is that if you put in more compactive energy, kind of going up this scale here, this is density. you'll increase the density of the soil. That's why there's these terms like a standard proctor, which is certain energy, and a modified proctor, which is more energy, and you get a higher density, like a T99 and T180 if you work with that. And different soil types have different characteristics and different compaction curves. A clay soil will ultimately have a lower maximum density and a higher moisture content. You're going to want to compact it maybe at 15 to 20% moisture to really facilitate good compaction. Whereas a gravel, way over here, is going to have a much higher final density, but you do it at a much lower moisture content, maybe 5 to 8% optimum moisture. If you're close to optimum, you can get good compaction. If you're way wet of it or way dry of it, you have trouble getting compaction. So if you have a contractor telling you that he can't get compaction on his soils, check and see where your moisture content is, because if it's too wet or too dry, then you understand why he can't get the compaction. But if it's got the optimum moisture, then you should be able to achieve it if you could achieve it in the lab, and if that was representative of what you have on the ground. Okay, and drainage. I'll say this the last time I think I'll say it in this series here is you've still got to have good drainage. If you've got water standing in your material, you just can't compact it. You can't have a firm subgrade. Okay, the last topic I'm just going to spend a few minutes on here is quarries. Like I say, if you can have a site near where you're working, you can save yourself a lot of money. But there's a lot of issues with quarries. One, you've got to have enough material, the quantity and quality of material. There's a lot of environmental and regulatory issues you've got to deal with today, so it's not easy to get new quarries on. There's a lot of development issues you need to think about, and you need to be thinking about reclamation. Here in California, you've got anything you do along this line, you're dealing with SMARA, the Surface Mining and Reclamation Act, that will dictate what's got to be done to develop a site or whether it's suitable. Part of it depends on finding what's available and then how you develop it. A lot of development issues, the space issue. Can you get away with just screening? Do you need 2 or 3 stage crusher? Do you need drilling and shooting in the first place? Will it come out okay if you have a good shot, oversized material versus a broken down material, depending on what you want? So those are kind of operational issues. And here's an example of a pit development plan. It's something that's required by SMARA, something that's required in our Forest Service manuals, and to me it's just good site management. And what you're saying is, how is this operation going to work? Where am I going to take out the materials? Where am I going to put the materials stockpile? How much area do I need? Can I stockpile topsoil over here for future reclamation work? Do I have room for access, or how do I get into the site? Down here in this cross section, what do I want it to look like when I'm done? Do I want to leave a pond here? Do I want to leave it draining? Do I want to leave a steep back slope here, or do I want to leave it really flattened out for public safety? These are all issues that are operational, but they also affect the reclamation of a site, particularly conserving like the topsoil that's got the organic, the seeds from the local site to help promote revegetation, and what the slopes look like, which affect both safety and erosion in the site. So every pit plan's unique, but I think every quarry ought to have one, and it is required here in California, as I understand. Operation where you're taking out of one part of the pit, reclaiming another part of the pit if it has a long-term use. There's visual impacts of both during operation and reclamation. Ponds, do you want to leave a pond? Do you want to drain it or leave it dry? Things like that. So there's a lot of environmental issues that affect both the operation and development and the reclamation of a site. And every quarry is unique. So but again, a lot of money can be saved by having a quarry close to a project. So there's a lot of benefits to having materials, but it's a mine. It's a big environmental impact. Last couple of photos here of doing some reclamation work, spreading some organic material out on a pit we took a lot of material out of, and when it was all said and done, it looked like this, kind of a park-looking atmosphere. But after we regraded it, reshaped the terrain, reseeded everything with local native grasses. Here's a site that was along Highway 70 in the Feather River Canyon, if anybody is familiar with it. We took about 15,000 yards out of here for a storm damage repair project because there was no other site. But then it was re-flattened here, reseeded, replanted some of these trees here. So it doesn't quite look like the natural forest, but it'll favorite reclamation picture. If any of you have ever been to Vancouver, or Victoria, British Columbia, this is in Burchard Gardens. Just a gorgeous site. This is a reclaimed old limestone quarry for producing of I guess, cement. And so it kind of shows what you can do with a quarry if you have time, money, and the will to do it. Few textbooks or publications. This agate design is by people and/or a Forest Service person. It's got a lot of good information on agate management and design. This Gravel Roads is a very popular federal highway publication done by actually South Dakota LTAP, Kim Skorthus and Ali Salim. This is a couple of Forest Service publications that have a lot of information on a variety of things, but deal with roadway materials and drainage. This publication here from Penn State on environmentally sensitive maintenance of dirt and gravel roads by that Center for Dirt and Gravel Road Studies at Penn State has a lot of good information. So these are all pretty good publications that deal with this. And last here are just a few questions of what is important about materials. First, you want to know what your soils and traffic are because that affects your design a lot. And then you choose the appropriate standard depending on that traffic, probably more than anything. If you're using aggregate, you need to make sure it's appropriate gradation or you have to compromise on poor quality material. Sometimes you do some in-place stabilization, but we've typically found that aggregate is usually the more common solution if you have aggregate available. Local materials may be marginal, but for low-volume roads and low-use roads, they're very cost-effective, but there's still always this quality control component that needs to go into materials, and that involves sampling and testing of the materials. Compaction is probably the cheapest way to improve your soils and aggregate. Got to have drainage. I guess I did say it one more time, didn't I? Okay, drainage is always a key issue, and last but not least, quarries. They save a lot of money, but there can be a big environmental and social impact. So the processing, the operation, the permitting can be pretty thorny, but there's a lot of money that can be saved. And in the long run, if you're developing a quarry, make sure you've got a reclamation plan and put it to bed. So that's it on materials. A lot of different aspects to materials. So I hope thanks for bearing with me on this.
Well, Gordon,